Hello there and welcome back to the Sleep Science. Tonight's topic is as warm as it is unsettling, and I mean that quite literally. We're drifting up close to our local star, the sun, and NASA's been whispering a few things lately that might make your eyebrows twitch. Picture this. You're standing in a snowy field, one of those crisp winter mornings where the cold practically sings through your coat, and then, bam, the sky flickers with green ribbons of aurora dancing somewhere they definitely shouldn't be. That's not just pretty, that's a solar warning shot. And no, this isn't science fiction. This is just solar physics, mid-simmer. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from now and what time your local stars came out tonight. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're walking slowly now, pacing through the shadows of recent data, because NASA, good old tight-lipped, protocol-loving NASA, dropped a quiet but chilling update a few weeks ago, tucked into a low-key heliophysics webinar and a handful of slides that never made mainstream news. Turns out the sun is waking up faster than expected. And not just waking, stretching, flexing, and flaring like it drank one too many espressos. We're currently inside what's called Solar Cycle 25. Think of these cycles like the sun's version of a mood ring that resets every 11-ish years. During a solar minimum, the sun calms down, its surface smooth and relatively quiet. Wait, but then it ramps up toward maximum, a period packed with magnetic eruptions, flares, and storms that ripple through the solar system like tantrums across the playground. And this cycle, well, it's already outpacing its own projections. NASA's official models predicted a modest uptick in activity, but what we're seeing? It's double the sunspot counts they anticipated for this phase. Imagine that, a star 93 million miles away having such a chaotic morning that it disrupts radio towers, overheats satellites, and starts debates among scientists who've studied it their whole careers. Historians still argue whether humanity has ever really experienced the sun at full unfettered rage. The 1859 Carrington event might have just been a solar sneeze. What's even more deliciously creepy is that NASA didn't issue a press release about these changes. No flashy announcement, no press conference with dramatic sunburst animations, just silent adjustments to their charts, and then back to regularly scheduled programming. It's like watching your doctor silently scribble something on their clipboard and then smile too brightly. That silence might be strategic, or it might just be caution, but either way, you're left imagining the implications alone. In the dark, one hand resting on your phone, that very much depends on satellite positioning. Now, to be fair, it's not just NASA noticing this acceleration. Independent observatories in Japan, Europe, and South America have confirmed similar anomalies. Solar flares blooming earlier and brighter, sunspot groups clustering with odd geometries, and even coronal mass ejections, CMEs, that move faster than our current models can comfortably explain. One solar physicist compared the current activity spike to watching a toddler sprint before they've learned how to walk, which sure sounds adorable, until that toddler is a 1.4 million kilometer wide nuclear reactor. A lesser-known tidbit, the increase in solar activity has already caused more visible aurora borealis sightings as far south as Texas and Madrid in the last year than in the entire previous solar cycle. Which sounds beautiful, until you realize auroras are just Earth's magnetic field frantically trying to deflect highly charged particles. It's like watching your umbrella scream during a windstorm and thinking, wow, what a pretty color. Here's where things get trickier. Our sun isn't just heating up externally, it's exhibiting internal anomalies too. NASA's Helios-ismic and magnetic imager picked up deeper solar oscillations than expected. Basically, quakes inside the sun's core. These Helios-ismic hiccups are like the star's version of burping mid-rotation. Scientists don't fully know why they're happening more frequently, but one fringe theory gaining traction? That our star's experiencing magnetohydrodynamic turbulence beyond what's typical for this phase of the cycle. Try saying that 3 times fast. NASA, of course, is cautious. Officially, they still categorize this cycle as within tolerable ranges, which is like your dentist telling you the tooth might not need a root canal yet. But unofficially, between minor data leaks and behind-the-scenes chatter among researchers, there's growing unease. Not panic, just that slow, a tightening feeling in the gut when the variables start refusing to behave. And remember, this isn't just a science issue, it's a people issue. Every power grid, satellite system, and airline route planning software quietly assumes the sun won't throw a tantrum this year. But now you know it just might. In fact, it's warming up its arms as we speak. And here's one for your dreams. A very old, obscure Russian weather balloon program from the 1950s recorded atmospheric ionization spikes eerily similar to what we've seen during the last few months. Their notes were dismissed at the time as equipment error, but now with modern sensors picking up comparable patterns, a few quiet scholars have started revisiting those dusty Soviet data logs with fresh, nervous eyes. Because when it comes to the sun, nothing is obsolete. So tonight, while you're drifting towards sleep, maybe let your mind float a little closer to that star that anchors our lives. It's ancient, it's magnificent, and it might just be getting cranky. The kind of cranky that scrambles power grids, fries satellites, and paints the sky with eerie green flames. And NASA? Well, they're watching. Quietly, carefully, probably while sipping government-issue coffee and wondering how to phrase the next update without spooking the interns. You're deeper now, drifting through soft plasma and strobing sunlight as if the sun were less a celestial body and more a rumbling engine in a garage you weren't supposed to enter. It's humming louder than expected, and the door's locked from the inside. Welcome to Solar Cycle 25, the current chapter in the sun's recurring 11-year magnetic mood swings. It began in December 2019, barely a headline amid the noise of that year, and most experts predicted it would be tame, predictable, mild. But like everything else since 2019, this one had other plans. See, NASA and NOAA jointly managed solar forecasts using a blend of historical records, computer simulations, and, you guessed it, sunspots. Those little black freckles on the solar surface are actually sites of intense magnetic activity, areas where the sun's own field lines get twisted and pinched, breaking open with explosions of energy. The more sunspots, the more action. It's kind of like acne, but for a giant burning gas ball. Back in 2020, NASA's Solar Cycle 25 prediction panel confidently said this cycle would be about as active as the last one. Nothing to worry about. But by late 2022, the real numbers began to overshoot the predictions. By a lot. Like a high school student saying they'd probably get a B and then accidentally inventing time travel during the final exam. Right now, the observed sunspot numbers are nearly double what models had projected for this stage of the cycle. That's not just an oops, it's a red flag in the heliophysics world. It means the sun is more energized, more magnetically complex, and more likely to hurl unpredictable tantrums toward Earth. In other words, this isn't just a warm-up. It's a headliner show arriving early, and the band is not sticking to the set list. Historians still argue whether we even understand solar cycles properly. Some researchers believe the sun follows a longer, hidden pattern, a grander rhythm that spans centuries rather than decades. The idea is controversial. It's partly because we've only had reliable solar data since the invention of the telescope in the 1600s. And let's be honest, Galileo wasn't exactly live streaming sunspot charts on Twitch. Still, there's enough sketchy evidence in the historical record, crop failures, unexplained auroras, failing compasses, to suggest that the sun occasionally does something big. Something we haven't seen in modern times. The Maunder minimum, for example, was a 70-year stretch in the 1600s where sunspots basically vanished and Europe froze under brutal winters. Some now wonder if the opposite, a supermax, not a minimum, could be on the horizon. One fringe detail that started getting traction among solar nerds is the return of active regions that resemble patterns not seen since solar cycle 19, which peaked in 1957 during the height of Cold War paranoia. That cycle remains the most intense ever recorded. Back then, radio blackouts were common, auroras shimmered over the equator, and military communications got so scrambled that the U.S. briefly mistook a solar flare for a Soviet nuclear strike. True story. Some officials were this close to retaliating with actual warheads. It's the kind of event that makes you wish the sun came with an off switch, or at least a polite warning. But here's where it gets even weirder. These cycles aren't clockwork. They're lopsided, irregular, sometimes skipping beats like a heart with too much coffee. Scientists have always struggled to forecast them with accuracy, but solar cycle 25 seems particularly squirrely. Some models show it peaking early, in 2024 or 2025, while others suggest it might have multiple peaks. It's like a volcano that keeps puffing smoke long after the eruption. NASA has quietly updated its timelines, shifting expected maximum dates without much fanfare. It's all there if you dig. Slide decks from heliophysics conferences, updated graphs on obscure research pages. But no one's waving red flags on primetime news. Not yet. And you're just lying there in the dark, breathing slowly, listening to the sun do its quiet little freak out 93 million miles away. Comforting, right? There's a calm tension to it all. This awareness that something enormous and ancient is turning just a bit too fast. It's not panic, not dread, just suspense. The implications of a stronger than expected cycle are hard to overstate. Solar max is when we get the bulk of our CMEs, geomagnetic storms, satellite anomalies, and radiation spikes. So if this cycle's ramping up early and hard, everything on and around Earth that depends on tech, which is basically everything, gets more vulnerable. Fringe idea of the night? Some researchers believe that solar cycles influence more than just tech. They point to obscure correlations between heightened solar activity and human behavior, spikes in migration, political unrest, even aggression. It sounds a little woo-woo, sure, but the data's been poked at for over a century. One Russian scientist in the 1920s, Alexander Chizhevsky, charted revolutions in solar flares side by side and claimed there was a connection. Mainstream science rolled its eyes. But others? They're still quietly watching. It makes you wonder. If the sun goes hyperactive, does Earth's entire rhythm shift? Not just electromagnetically, but emotionally, biologically. Are we that connected to our star? Or is that just romantic sci-fi talking? Either way, Solar Cycle 25 is officially a wild card, and the folks at NASA know it. They're watching sunspots form in configurations they haven't seen in decades. Huge, complex magnetic loops with the potential to snap and send plasma blasts hurtling toward Earth at 1,000,000 miles per hour. That's not poetic exaggeration. That's actual CME velocity. And in the silence between flares, when the sun's surface seems calm, there's this sense of waiting, like the next act hasn't started yet, but the orchestra's tuning up, and someone backstage just knocked over a drum kit. So yeah, Cycle 25 is heating up early, and no one knows exactly how hot it'll get. You're still floating in that slow solar gravity, warm, weightless, watching the skin of the sun ripple like liquid gold under a windstorm. But then you notice the freckles. Dark blotches scattered across the light, like bruises on an orange peel. And suddenly you're back on Earth, staring at satellite photos that look more like ink spills than scientific data. Welcome to the strange return of sunspot spaghetti, those tangled magnetic messes NASA's quietly been updating its models for. Sunspots, those moody little dark patches, aren't just pretty patterns. They're warning signs. Each one is a marker of twisted magnetic fields, a place where solar plasma can erupt into flares or ejecta. And lately, they're not just returning, they're multiplying in complex, uncooperative ways. The spaghetti part? And that's what NASA scientists unofficially call the forecasting models now. Because the paths of sunspot growth and flare probabilities look less like neat graphs and more like tangled noodles tossed across a chalkboard. Predictability? Gone. Order? Laughable. And just like spaghetti, some of these sunspot clusters stretch in long, winding lines, multi-region arcs that look like they were scribbled by a caffeinated toddler. In late 2023, one such megacluster, dubbed AR3460, wrapped across over a quarter of the solar equator. It was so long that when one end flared, the ripple echoed across the rest like a magnetic whip. NASA's Solar Dynamics Observatory caught the event in crisp detail, but the real story was buried in technical updates, Small addendums noting that previous modeling parameters may underestimate event chaining. Translation? We, the sun, might be playing dominoes with sunspots, and we've barely begun to grasp the rules. Historians still argue whether the ancient Chinese and Mesopotamian astronomers recorded sunspots during times of empire collapse. Some think those meticulous stargazers were seeing solar maxima in action, cycles of light and dark that mirrored human unrest. But even now, with all our fancy sensors, the exact mechanics of sunspot group behavior remain a murky pool. That's what makes the recent changes so unsettling. See, normally sunspot clusters form, evolve, and decay in fairly linear sequences. But NASA's been quietly tracking something new. Nonlinear fusion events, where two or more sunspot regions merge instead of fading. Think of it like a weather system that eats another storm instead of drifting apart. One such fusion event in early 2024 resulted in a flare nearly 10 times stronger than initial forecasts suggested. Not the kind of surprise you want when your satellites are out there dodging debris like space rodeo clowns. You also get these so-called delta spots, sunspots with mixed polarity magnetic fields, where north and south poles coexist in chaotic proximity. And guess what? Cycle 25 is generating more delta spots than the last 3 cycles combined. These are flare factories, plain and simple. The kind of configurations that have solar physicists double-checking backup power for observatories. It's now for your fringe treat of the night? Some researchers are suggesting that these increasingly tangled sunspot patterns might be tied to activity beneath the sun's surface, deep magnetic shears that aren't part of the usual 11-year heartbeat. It's speculative, sure, but one theory proposes a secondary 200-year magnetic cycle overlapping with the usual one. And when they interfere, you get exactly what we're seeing: twisted, unpredictable behavior on the surface. Which brings us to one rather awkward truth. NASA's modeling software, Magneto and Adapt, for those of you whispering nerd words in your sleep, wasn't really built for this level of chaos. It's like trying to track a tornado with a paper map and a spoon. So while public-facing graphs show nice, smooth sine curves of rising sunspot activity near the back-end data being shared between solar labs, it's messy, complex, and increasingly worrying. And yet, no alarms, no late-night presidential briefings, we hope. Just quiet recalibration and a flurry of footnotes. You might think, okay, so the sun's being moody. What's the worst that can happen? Bad Wi-Fi? And yes, technically. But it's more than that. These erratic sunspot formations are a direct precursor to solar flares and coronal mass ejections, the real teeth of solar storms. And when clusters become too complex to predict, it means those teeth can bite without warning. That's what happened in mid-2023 when a mid-level sunspot cluster, barely registering on predictive charts, suddenly flared into an X-class burst, the highest category of solar flare. The resulting storm disrupted shortwave radio in the Pacific for several hours and degraded GPS signals across multiple continents. Pilots reported compass drift, hikers got hilariously lost, and a Norwegian cruise ship reportedly lost satellite communications for nearly 6 hours, forcing the crew to navigate by actual stars. Somewhere, a sailor smiled. Here's a fun historical throwback. During World War II, British radar systems suddenly lost function across the coast for several minutes. They thought it was German jamming. Turns out, it was a solar flare, one of the first to be captured by radio instruments. Historians still argue whether Churchill ever got briefed on the solar cause, or whether he just muttered something about tea and moved on. And now, over half a century later, we're still dealing with the same invisible menace. Only now our entire civilization runs on fragile digital pulses. The wild thing is, for all the sun's fiery theatrics, most people won't even notice. You'll be driving to work, or watching a video in bed, or trying to reheat your soup, and overhead the sky will momentarily twist with invisible storms. Somewhere a satellite will twitch, a plane will pause, and a solar physicist will mutter, "Well, that wasn't in the spaghetti." And you'll just be lying there, warm in the dark, hearing the subtle churn of a star that's starting to pull new tricks. Unreliable tricks, because when the sunspots go spaghetti, It's only a matter of time before the sauce hits the fan. You're still drifting, lulled by plasma waves and whispering radiation. But now the sun isn't just boiling, it's talking. Not in any language you'd understand exactly, but in the sharp chirping frequencies of Type 3 radio bursts. And these? They're not just background noise, they're alarms. See, every solar flare is a shout, but some of those shouts come with radio signals, brief, high-speed screeches that race through space faster than the plasma that caused them. And lately, there's been a lot more of these high-pitched outbursts. NASA quietly cataloged a sharp uptick in Type 3 bursts over the past 18 months. They didn't make headlines, but in heliophysics circles, it was like hearing the fire alarm get tested every other day. You're lying there in the quiet, and if your ears could hear in megahertz, the sky would be full of static whines and digital shrieks. Because Type 3 bursts are caused by fast-moving electrons shooting along magnetic field lines during a solar flare. They spiral outward from the sun at near-light speed, racing ahead of the ejected material like cosmic scouts. The bursts themselves only last a few seconds, but they're loud, at least to the antennas that know how to listen. And NASA has been listening. Using instruments aboard spacecraft like the WIND satellite and the stereo pair, scientists have been logging these radio screams and quietly recalibrating what they mean. Because here's the twist. We're hearing more of them from smaller flares than ever before. Flares that wouldn't normally be considered dangerous are suddenly screaming like banshees through the solar system. Historians still argue whether ancient civilizations may have heard solar radio noise during intense storms. Some legends speak of sky song or celestial whistling. That might sound poetic, but during the Carrington event of 1859, some telegraph operators did report hearing strange hissing sounds as their lines sparked and melted. So maybe the sun's voice isn't just metaphorical. Maybe it's electromagnetic. Here's a juicy fringe theory to chew on while you drift. Some researchers believe these Type 3 bursts could be used as a kind of solar early warning system, a sort of interstellar radar ping. Because they travel so much faster than the particles in a coronal mass ejection, these radio signals can reach Earth minutes, or even hours, before the physical storm arrives. That's like hearing thunder before seeing lightning, only in reverse. So NASA's been fine-tuning its instruments to interpret these screeches in real time. Not just to say, hey, something happened, but to guess what kind of storm is coming behind it. It's a bit like hearing the pitch of a dog's bark and guessing whether it's running or just howling at the moon. Here's where things get deliciously eerie. In 2023, a small, seemingly ordinary solar flare produced a radio burst so strong that it temporarily jammed a decommissioned Cold War military antenna in Greenland. The antenna wasn't even active. It was in storage, part of a frozen relic field used for calibration experiments. But it lit up like a Christmas tree. Nobody was expecting that. Not even the researchers who'd been monitoring that frequency range. NASA downplayed the event as anomalous signal reception. But in internal reports, the chatter picked up. Why are minor flares producing major bursts? Some speculate that the sun's magnetic field is forming resonance layers, zones where trapped energy echoes and amplifies outgoing signals. Others wonder if Earth's changing ionosphere is becoming more sensitive than we thought. Either way, the Type 3 burst rate has risen by more than 30% compared to the same period in the last cycle. The sun's voice is getting louder, or maybe just more desperate. You wouldn't notice, of course, not unless you were one of the small community of amateur radio operators. Yes, they still exist, who tune into the solar bands like cosmic DJs. Some of them reported ghost noise during minor storms, hissing, fluttering, even rhythmic pulses. Not music, not speech, just the sun's static lullaby. Fun fact? The first Type 3 bursts were discovered by accident in the 1950s, when scientists at the Naval Research Laboratory picked up strange noise on a solar telescope they had only just finished building. It was like turning on a new microphone and immediately catching someone whispering your name. Today the signals are clearer, but what they mean, that's still up for debate. One of the newest instruments tracking these bursts is aboard NASA's Parker Solar Probe, a spacecraft that's diving closer to the sun than any object we've ever built. It flies through the solar wind itself, brushing against the corona, and it hears these bursts from inside the source. and what it hears sometimes doesn't match what we detect from Earth. And that discrepancy has scientists quietly wondering, are some solar signals getting lost or distorted by Earth's atmosphere before they reach us? And if so, what else aren't we hearing? Parker's data logs have revealed layered radio patterns like overlapping screams coming from complex flare events. Some even appear to have repeating structures, almost like Morse code. No, don't get excited. We're not talking aliens. But we are talking about self-organizing plasma behavior, something that's still not well understood. And if the sun's talking in code, even unintentionally, it might mean our models need to learn a whole new language. NASA's current challenge? Building real-time predictive systems that can decode these bursts fast enough to issue warnings, not just for astronauts, but for power grids, GPS systems, even airplanes. And because a big enough flare, preceded by a loud enough burst, might be the only warning we get before the lights flicker and your phone can't find a tower. And all the while you're lying there, peacefully unaware that the sky is full of whispers and wails. Because the sun doesn't just shine, it sings, loudly, strangely, and with increasing urgency. So the next time you glance at a cloudless sky and think it's silent out there, know that above the blue, the sun is screaming into space. And NASA? NASA is listening. You're still weightless, suspended in that hazy gold where science meets unease. And now the sun isn't just talking, it's twisting. Picture magnetic fields writhing across its surface like invisible ropes pulled taut, then snapping with a crack that sends fire sailing through space. This isn't just heat. This is magnetic chaos. And NASA's been quietly shifting its tone about what's really happening up there. Every 12 minutes or so, somewhere on the solar surface, magnetic field lines cross, reconnect, and release energy. It's a normal process, like breathing, for the sun. But lately, the patterns have changed. These magnetic loops are larger, more complex, and flaring more violently than predicted. NASA's latest solar imagery shows loops taller than Earth itself, pulsing in slow motion like muscle contractions across a star that shouldn't have muscles. In the past, you could more or less chart these eruptions, solar flares and coronal mass ejections, CMEs, by tracing where two or more field lines intersected. Clean, predictable. But Cycle 25 has gone rogue. Now the magnetic ropes form tangled braids, compress, snap, and reform without warning, start creating what NASA politely refers to as impulsive reconnection events. Translation? The sun's throwing tantrums, and it's doing it without following the usual rules. Historians still argue whether similar magnetic twists may have caused the unusual auroral storms recorded by Babylonian astronomers. Some translated those stone tablets to mean fire serpents in the sky, which frankly isn't too far off. The fringe tidbit tonight? A group of theoretical physicists recently proposed that some of these chaotic magnetic eruptions might not be entirely random. According to their model, the sun's deeper magnetic dynamo, buried beneath the photosphere, could be cyclical, sending up nested spirals of energy at regular but misaligned intervals. Like two gears grinding against each other, occasionally locking up, then releasing in sudden, furious bursts. That idea is controversial, of course. Not everyone's ready to admit that the sun may have a hidden internal heartbeat layered beneath the cycle we already know. But if it's true, it means every once in a while, the sun goes briefly, magnetically insane. NASA's own Solar Dynamics Observatory has picked up evidence of magnetic helicity, twisting structures that don't just break, but spin out of the sun like solar tornadoes. One particular event in early 2024 caught their attention. A triple helix magnetic structure erupted over 36 hours, flinging hot plasma in a spiraling corkscrew that traveled millions of miles. The resulting CME reached Earth 3 days later, sparking minor geomagnetic storms and major discomfort in the modeling community, because no one saw it coming. And the magnetic fields involved were too complicated to trace in real time. This wasn't a clean two-point reconnection. This was magnetic spaghetti going airborne. And the worst part, these tangled structures don't always produce warning flares beforehand. Sometimes they just go. No precursor, no blip. Just boom. That's a problem, because traditionally flares act as a kind of solar heads up. You see an X-class flare, you brace for impact. But with these complex reconnection events, the CME might already be halfway to Earth before we even know the sun moved. It's like waiting for the microwave beep and realizing your popcorn's already exploded all over the kitchen. You're probably wondering what all this means for your daily life. You, the grounded human, snug under a blanket, listening to this from beneath the ozone layer? Well, for one, it means space weather forecasting just got harder. Way harder. NASA has quietly revised its flare prediction models, especially the ones used by satellite operators and flight planners. But here's the unsettling part. They're now issuing more short-term watches, more possible disruptions, more precautionary repositioning maneuvers. Behind the scenes, the satellites you rely on for GPS, weather, and streaming those oddly satisfying tile-grouting videos are being told to brace more often. And if you think that's just affecting science stuff, think again. Earlier this year, a small CME from one of these twisted reconnection events caused temporary disruptions in satellite communication over the Indian Ocean. For 2 hours, shipping routes went dark. Autonomous cargo vessels drifted slightly off course. Planes had to switch to backup inertial guidance systems, and one commercial flight reported a 5-minute compass lag mid-descent. 5 minutes. In the wrong hands, that's more than enough for a disaster. Now, for a weird historical callback, in 1972, during the height of the Vietnam War, a solar storm disrupted American naval mine sensors in the waters off Haiphong. Some of the mines detonated spontaneously, triggered by magnetic fluctuations in the water. Historians still debate whether the Navy ever connected that to the sun, but modern military satellite logs now routinely cross-reference solar flare data before scheduling sensitive operations. Because you never want to blame the sun for blowing something up until it happens again. Now picture this. 2 magnetic ropes, each the size of North America, were twisting around each other like angry pythons. For hours, days. NASA watches, hoping they'll untangle peacefully. But then, snap. A loop breaks. Plasma jets outward. A CME is born. And here's the kicker. Even NASA's best predictive systems can't always tell where that plasma will go. Sometimes it misses Earth. Sometimes it hits us head-on. Sometimes the solar wind deflects it in mid-flight like a cosmic curveball. You're just watching the clouds. You don't see the space tornado headed your way. What's scarier? These tangled reconnection events are becoming more common, more frequent, and they seem to be happening earlier in the cycle than expected. We're not supposed to see this kind of solar gymnastics until the peak, maybe 2025 or 2026. But here we are. NASA's own charts have been quietly redrawn, not in red alert colors, and of course, just subtler curves, tweaked captions, revised thresholds. Because shouting about magnetic chaos rarely goes over well at congressional budget hearings. But still, the sun is misbehaving. Its magnetic playground is no longer safe or quiet or polite. And behind those glorious solar images you see online, those swirls of gold and crimson, are tangled forces snapping and flinging plasma like angry gods with slingshots. So next time you glance up at a blue sky and feel a little too warm, remember, heat is the least of it. The real story? The sun's magnetic fields are playing a game of cosmic cat's cradle, and the strings are starting to break. You're still floating there, but the heat now feels heavier. Not from fire, but from pressure. Invisible, persistent, a slow compression wrapping around Earth like a hand on a balloon. Because while the sun flings its tantrums, Earth's invisible umbrella, our magnetic field, is taking the hits. And NASA, very quietly, is starting to admit that we're not bouncing back the way we used to. You may think of Earth's magnetic field as a kind of invincible shield, a superhero cape flaring out into space to deflect whatever solar nonsense comes our way. And that's mostly true, but like all superheroes, even this one gets tired. And over the past few years, scientists have been quietly compiling data that shows Earth's magnetic field isn't just fluctuating, it's weakening, and more often than anyone expected. Let's break it down. When the sun belches out a coronal mass ejection, one of those big plasma storms we talked about, it slams into the Earth's magnetosphere like a wave against a seawall. Normally, that wall bends, flexes, she then recovers. But lately, recovery has been slower. Sometimes parts of the magnetosphere stay compressed for days, exposing higher regions of the atmosphere and everything in them to increased radiation. NASA's Magnetospheric Multiscale Mission, or MMS, has been watching this happen in real time. Using 4 formation flying spacecraft, MMS studies magnetic reconnection in Earth's outermost field layers. And the data? Not exactly cheerful. It's showing more frequent breaches in our magnetic boundary. Not catastrophic holes, just thin, temporary rips that let in solar particles like a screen door in a hurricane. Historians still argue whether this weakening is part of a long-term magnetic pole reversal, the kind that happens every few 100,000 years. Earth's magnetic north has been wandering faster lately, sprinting across the Arctic at rates we haven't seen before. Some say that's just a fluke. Others, quietly wondering if we're overdue for a total flip. And during a flip, the shield gets patchy, confused, maybe even collapses for a while. Now, before you swan dive into doomsday mode, it's worth noting, pole reversals have happened many times before. The Earth didn't explode. The dinosaurs didn't immediately perish, unless you count a certain asteroid. But back then, no one had GPS satellites, transpolar flights, or astronauts chilling on the International Space Station. And here's the part NASA didn't exactly tweet. The South Atlantic anomaly, a weird, weak patch of magnetic field stretching over South America in the southern Atlantic, is growing and deepening. Satellites passing through it regularly report increased radiation exposure. Some even glitch. Space telescopes have to turn off sensitive instruments when flying through that region, just to avoid frying delicate electronics. It's like the Earth's protective bubble has a soft spot, and that soft spot is getting thinner. In fact, fringe researchers have speculated that if the anomaly keeps expanding, we might have to reroute satellites entirely around it, changing orbital inclinations, altering launch plans, and potentially redrawing our entire communications infrastructure. That's not a casual shift. That's redoing the plumbing of space. And the astronauts? Yeah, they've noticed too. During periods of heightened solar activity, radiation levels aboard the ISS spike as the geomagnetic field bends under pressure. NASA's been quietly updating its radiation protocols, while issuing revised exposure guidelines for both short and long-term missions. One internal memo even suggested installing new storm shelters inside future space stations, areas lined with water or polyethylene to block charged particles during severe solar events. Because if Earth's shield is buckling, you don't want to be orbiting without an umbrella. Here's your quirky fact for the night. Birds can sense the magnetic field. Some migratory species have built-in compasses using magnetite crystals in their brains. Lately, a few ethologists, yes, that's a real word, have noticed more navigational errors in birds flying across geomagnetically unstable zones, flights veering off course, migration patterns getting weird. Maybe it's just coincidence. Or maybe the birds are warning us in the only way they know how, by getting a little lost. Meanwhile, back on the ground, the magnetosphere still protects us from most of the sun's fury. But that protection isn't infinite. Strong enough geomagnetic compression can cause ground-induced currents, tiny surges that slither through the crust and into power lines. During major solar storms, those currents can overload transformers, pop breakers, and shut down entire regions. It's already happened. In 1989, a geomagnetic storm knocked out power across Quebec for 9 hours. 1 million people went dark. No phones, no heat, no lights. That storm? Modest by Carrington standards. And NASA's models, updated quietly in mid-2025, suggest that Earth's magnetic field is now more susceptible to similar compression events. Not because the storms are bigger, though they are, but because the shield itself is softening, like old Kevlar stretched too thin. Why is this not headline news? Well, it's slow, uneventful, hard to photograph. You can't take a selfie with a weakening magnetosphere, but the signs are there, in telemetry reports and geophysics journals, in the gentle rephrasing of NASA's mission statements. in the increased frequency of test alerts that suspiciously resemble real ones. So you're lying there staring at the ceiling, and somewhere far above your head, the sky is crackling with electricity, magnetic fields bend, plasma streams, and the Earth, brave little sphere that it is, continues to hold the line. But the umbrella's getting threadbare. So next time your compass app glitches or the aurora flickers in a place it shouldn't, remember? You're watching the magnetosphere flinch. And the sun? It's not done pressing. You're still riding the ripples, watching Earth's magnetosphere bend under solar breath. But now, down below, the effects are getting personal. No more invisible lines or abstract models. This time, the sun's moods are reaching into your actual human life. We're talking about planes rerouted, GPS wandering, and a kind of digital déjà vu that's quietly building into the background hum of modern life. Let's start with a simple picture. You're flying at 35,000 feet, gliding through the polar skies, sipping bad coffee and wondering if turbulence is the price of air travel or just karma. But what you don't see is the invisible wall of solar radiation building ahead. And neither do the pilots, until suddenly the comms flicker, the compass drifts a few degrees, and a quick, quiet message comes through. Reroute required. And this isn't science fiction, it's already happening. Since early 2024, transpolar flights, those long-haul shortcuts between continents that skim over the top of the world, have been rerouted more frequently due to elevated radiation levels in the polar atmosphere. NASA, working with the FAA and international aviation authorities, has quietly flagged the increase in space weather-related flight path deviations. The reason? During geomagnetic storms, charged particles flood Earth's polar regions, slipping through the weakened magnetosphere like clever burglars through a broken lock. These particles can interfere with radio communication, especially HF, high-frequency bands, which are still the go-to for aircraft beyond satellite coverage. When those signals go fuzzy, pilots and air traffic control lose contact, and nobody wants to fly blind over the Arctic. So what do? They divert, southward, longer routes, more fuel, delays, minor logistical nightmares. And it's not just once in a blue moon anymore. In 2025 alone, over 75 polar flights were rerouted due to space weather alerts, more than triple the annual average from a decade ago. Historians still argue whether early aviators in the 1920s noticed solar interference. Some pilot logs mention compass dancing and navigational ghosting during auroral nights. Back then, they blamed poor instruments. Now, we know better. The sky has moods, and the sun plays puppeteer. But it's not just planes in the crosshairs. Your smartphone's beloved GPS, the map that gets you to taco trucks, awkward dates, fun and suspicious hiking trails, is also feeling the squeeze. Global Positioning System satellites orbit in medium Earth orbit, roughly 20,000 kilometers above your head. And while they're designed to handle a bit of solar sass, the increased solar flux and expanding radiation belts of Cycle 25 have led to signal degradation during flare events. Translation? Your location might drift a little, or a lot. In 2024, during a mid-tier solar storm, several GPS receivers in Europe logged position errors of over 100 meters. That's enough to push a delivery van into the wrong driveway, or a drone into restricted airspace. Agricultural systems that rely on precision GPS for planting and irrigation saw rows go crooked. Self-driving tractors swerved. Someone's corn maze is now abstract art. And no, you probably didn't hear about it. Because the glitches were chalked up to software issues or unusual signal noise, which is true, technically. But the source of the noise, sitting there in the sky, boiling with quiet contempt. Even civilian traffic apps like Waze and Google Maps have quietly adapted. A few recent updates now include dynamic location smoothing, which basically guesses where you're probably going if the satellite signals hiccup. One developer forum even joked that they were teaching AI to hallucinate straight lines. But for more critical systems, like emergency response, aircraft navigation, or missile targeting, those errors aren't funny, they're dangerous. NASA's been coordinating with the US Air Force and the European Space Agency to develop rapid flare response models that can reweight GPS correction algorithms in real time. That's not a small task. That's a team of rocket scientists trying to teach space to lie less convincingly. Fringe tidbit: there's a growing movement of amateur radio operators and GPS hackers who track these anomalies live, building underground maps of solar interference zones. Some of them even claim to have predicted minor geomagnetic storms based on sudden shifts in their backyard antennas. It's part science, part hobby, and part beautifully paranoid. And then there's the jets. In August 2025, a commercial aircraft en route from Tokyo to Chicago reported a sudden heading deviation after a short, sharp magnetic fluctuation tripped its onboard inertial navigation calibration. The correction was automatic. The passengers never knew. But the post-flight report ended up in NASA's Space Weather Archive, marked as Type 3 anomaly, intermittent solar coupling. That's bureaucratic lingo for the sun pushed the plane sideways. It's not just science fiction anymore. This is the kind of low-key chaos that builds slowly, invisibly, under the radar, literally. And as solar activity continues to climb, the incidents are no longer edge cases. They're edging into the norm. Meanwhile, NASA's SWPC, Space Weather Prediction Center, has issued more alerts in 2025 than in the previous 3 years combined. Many are minor, G1 or G2 class geomagnetic storms, but more frequent, more persistent, like the sun's knocking, gently at first, but refusing to leave your doorstep. And the truth is, we're not as prepared as we think. Most infrastructure assumes occasional disruptions, not a whole era of heightened interference. While we're still using systems designed during quiet solar times, trying to make them hold up during this unexpected spike. It's like using paper towels in a thunderstorm. So you lie there, calm, unaware that a plane above your head is taking the long way home, that your phone might have just wandered a few meters east, that the sun's silent weather has become a daily variable in global logistics. And Earth just keeps orbiting, pretending that everything's normal. But the truth? Normal is changing, and the solar wind's now part of your forecast. You're still resting there, tucked beneath the invisible shield, but above your head, way up in that gleaming orbital highway, the machines we rely on are struggling. Not dramatically, not with explosions or fiery reentries. No, this is quieter, slower. Satellites are drifting, dragging, sinking, not even. And NASA, always measured, has been whispering what it really means. The sun is stealing our satellite's altitude. This is the side effect nobody likes to talk about. When the sun gets active, it doesn't just flare or scream with radio noise. It heats Earth's upper atmosphere, causing it to expand like a thermal balloon. It's called thermospheric inflation, and it creates drag where there normally shouldn't be much, which means satellites, even ones in fairly high orbits, suddenly find themselves pushing through a denser than expected soup of atoms. In early 2025, NASA and private satellite companies started noticing something peculiar. Satellites were losing altitude faster than projected. Nothing dramatic, just a few dozen meters here, 100 there, but enough to matter, enough to mess with orbital math. Enough to cause a small wave of emergency station-keeping maneuvers, quietly carried out by SpaceX, OneWeb, and several telecom operators. Want a specific number? Since mid-2024, orbital drag has increased by up to 70% during peak solar activity weeks. 70%. Let's put it another way. Your fancy Starlink dish might still beam internet through the storm, but the satellites above it, they're playing space pinball, quietly burning extra fuel just to hold position. And every time they correct their orbit, they edge one step closer to early retirement, because fuel in space is finite, and when it's gone, you're just another chunk of drifting metal. Historians still argue whether early Sputnik missions noticed drag anomalies tied to solar peaks, or if they were just too busy not crashing. But now, with thousands of satellites in orbit and mega constellations blanketing the planet, the stakes are much higher. In fact, NASA and the ESA have both quietly published new solar drag correction models, warning satellite operators that mission life expectancies may need to be shortened if solar activity remains this intense. One such report was slipped into an aerospace journal under the benign title, Thermospheric Variability, Implications on LEO Operations. Translation: the sun's mood swings are shortening your satellite's lifespan, and we're all politely pretending it's fine. Now here's a fringe twist for your dreams tonight. A group of independent researchers in Norway and Australia are tracking phantom sync patterns, unexpected orbital degradation in satellites that weren't supposed to be affected by drag at their altitude. The working theory? Transient bands of charged oxygen ions are forming in strange belts during certain geomagnetic storms, briefly extending the drag zone much higher than anyone predicted. It's unconfirmed, but if true, it means no orbit is safe during the wrong kind of flare, and there have been casualties. In February 2024, a batch of 38 newly launched low Earth orbit satellites, part of a commercial imaging network, failed to reach stable orbit. The company initially blamed deployment anomalies, but insiders leaked that the true culprit was unexpected atmospheric expansion caused by a stealth CME 2 days before launch. The spacecraft launched into thicker than predicted air, slowed too quickly, and re-entered within days. NASA's official statement: 1. Solar activity contributed to unanticipated orbital decay, which is science speak for the sun inhaled them. And it's not just new birds falling from the sky. Older satellites, those built in the 90s and early 2000s, are now seeing accelerated end-of-life drift. Many of them don't have the fuel reserves or maneuvering tech to compensate. Some are being quietly nudged into graveyard orbits. Others just left to slowly spiral downward, invisible space junk gliding toward incineration. You don't see the fireball, of course. It happens quietly high in the mesosphere. A flash, a smear of plasma, one less pixel on someone's global coverage map. Here's a quirky twist. This isn't all bad. Increased atmospheric drag also acts as a natural garbage collector for low-orbit space debris. All that junk we left up there, pieces of rockets, defunct CubeSats, that one wrench from a 1984 spacewalk, solar activity is pulling it down faster than expected. It's like the sun decided to help clean up its yard while knocking over the patio furniture. But even that silver lining has an edge, because more drag means more re-entry risk. Not all of these objects burn up fully. NASA now tracks hundreds of partially surviving pieces, fuel tanks, structural supports, mystery boxes, expected to make it to the lower atmosphere. Most fall into oceans or uninhabited zones. Most. There's an internal NASA protocol called Object Reentry Risk Assessment, or ORRA. Since early 2025, the number of elevated concern cases has doubled. That doesn't mean we're in Armageddon territory, but it does mean someone, somewhere, has quietly built a simulation for how to evacuate a square kilometer in under 90 minutes, just in case. And here's where things loop back to you. That map you loaded, that weather forecast, that satellite dish on your roof. Every one of those depends on a network of machines currently fighting gravity harder than expected. And those machines? Some of them weren't designed to live in a world where the sun turns up the thermostat and inflates the sky. So what is NASA doing? They're adjusting orbital models, issuing quiet drag alerts, collaborating with private companies on solar-smart satellite architecture, and above all, monitoring every flare, every storm, every twist in the wind. Because in this new solar cycle, space isn't stable. It's slippery. So while you lie there cozy and calm, 100 kilometers overhead, metal birds are struggling to fly, engines fire, trajectories shift. A silent war with friction plays out in the thermosphere. And the sun? The sun just keeps smiling. You're drifting higher now, beyond drifting satellites and glitching GPS signals, brushing up against the outer edge of human ambition. Because above it all, tethered to nothing but hope and alloy, are the astronauts. Real people in real suits, orbiting Earth in a thin canister of aluminum and science. And lately, thanks to the sun, their job has gotten a lot more dangerous. See, NASA doesn't like to panic. It especially doesn't like to panic when lives are literally floating in zero gravity. But tucked quietly into recent radiation exposure logs, buried beneath all the acronyms and technical phrasing, is something undeniable. The sun is hitting the ISS crew harder than expected. Cosmic radiation in space is always a problem. Without Earth's atmosphere to block incoming charged particles, astronauts live in a constant drizzle of space weather energy. But during solar maximums, that drizzle can become a storm. And during this particular cycle, solar cycle 25, that storm is coming early, strong, and loud. In mid-2025, NASA released an understated update to its crew health radiation tracking dataset. What it revealed, ISS personnel were receiving up to 22% more ionizing radiation than forecasted during certain solar flare weeks. That's not a rounding error. That's a mission-altering variable. Now remember, these aren't doomsday levels. Astronauts aren't glowing in the dark. But radiation adds up. Cumulative exposure increases the risk of everything from cataracts to central nervous system effects to cancer. NASA has strict dosage caps for astronauts, especially those on long missions. And right now, those margins are getting thinner. You probably didn't hear about it. No press conference, no dramatic photo of a spacesuited figure shielding their eyes from a sun flare. Just quiet adjustments to duty rotations and subtle tweaks in exposure windows. Onboard protocols have changed. Some experiments are now postponed during high flux periods. Crew members shift sleeping quarters to more shielded areas. Because in low Earth orbit, protection comes down to centimeters of insulation. The ISS is not a bunker. It's a tin can wrapped in optimism. Historians still argue whether early Apollo astronauts were lucky or reckless. Apollo 16, for example, passed through the Van Allen belts just days before a large solar particle event. Had the timing been different, the crew might have absorbed a lethal dose of radiation on their way to the moon. One NASA physicist later called it the closest near miss we don't like to talk about. Well, we're talking about it now. Fringe detail of the night? There's a growing movement inside NASA, and especially within private spaceflight circles, pushing for active radiation shielding. Not just more insulation, but electromagnetic field generators that could bend radiation away from habitats. It sounds like sci-fi, but it's based on real physics. The idea is to mimic Earth's magnetosphere on a small scale, a personal force field essentially. And a few prototype modules have been tested. So far, promising and wildly expensive. And then there's Mars, because while the ISS crew gets a front row seat to solar weirdness, NASA's eyes are on deep space, where shielding is even more limited and help is years away. Remember the MAVEN mission? That little spacecraft has been studying how solar wind stripped away Mars's atmosphere over billions of years. And the data? It's grim. MAVEN showed that solar storms literally eroded Mars's magnetic field, allowing particles to bombard the surface unchecked. One major solar event today could rip up another layer. And the implication for humans? Any future Mars habitat must be deeply shielded or buried underground, because a surface base during a strong CME is just an irradiated tin can in waiting. That's part of why Artemis astronauts won't be lingering on the lunar surface during active solar weeks. Yes, the moon has no atmosphere, but it also has no magnetosphere. During a flare, there's nowhere to hide but inside a lander, or preferably under meters of regolith. Back here in orbit, NASA's quietly upgraded its solar monitoring toolkit. The solar radiation storm alerts are now more granular, more urgent. They feed directly into mission control and issue real-time warnings. If a big flare is incoming, astronauts may need to pause EVAs, extravehicular activities like spacewalks, or retreat into shielded compartments designed for radiation storms. They call them storm shelters, not bunkers, not panic rooms. Just soft-line modules with extra water tanks and dense material walls. One such chamber, dubbed the beam module, was added in partnership with Bigelow Aerospace. It wasn't originally for radiation, but it's been adapted. Think of it as an inflatable life raft in orbit, only instead of water, it protects from pure energy. And just to make your dreams more interesting tonight, consider this. During one X-class flare in late 2024, the ISS passed through a region of intensified radiation so quickly that onboard dosimeters spiked before protocols could adjust. It only lasted 90 seconds, but it was enough to trigger a crew-wide shift to shelter mode and initiate a full health telemetry review afterward. You didn't hear about that either. But the data was there, if you looked. So what does all this mean for the average Earth dweller? Maybe nothing. For now, you don't live in orbit. You're not exposed to cosmic rays while brushing your teeth. But the astronauts are canaries in the space mine. They live at the boundary, where Earth's magnetic field starts to fade and the sun's mood becomes law. And if radiation is rising there, faster than expected, with stronger flares and more unpredictable solar storms, then every future mission, Moon, Mars, asteroid, or deep space station, is already at risk. Not dramatically, not explosively, just statistically. That's how space gets you. Not all at once, but in counts, rads, microsieverts per hour. You lie there in the dark, maybe thinking of the stars as peaceful lights. But up there, above the clouds, above the safety of atmosphere and aurora, people are sleeping under constant threat, breathing recycled air, wearing radiation badges like name tags. And the sun's just stretching, warming up. You're still hovering near the edge of orbit, just below the line where atmosphere fades into vacuum. And tonight, your sky glows. Not with sunlight, but with shimmering waves of green and violet, unfurling in ribbons across places that were never supposed to glow. Because now the auroras are wandering. They're showing up in the wrong zip codes. And NASA quietly rewriting the rules. You know auroras, those famous northern lights, scientifically known as aurora borealis in the north and aurora australis down south. They're more than just pretty. They're Earth's magnetic field visibly reacting to incoming solar particles. The collision of electrons with atmospheric gases produces that iconic glow. Green from oxygen, red from nitrogen, and purple when things get really frisky. Historically, auroras stay close to the poles, tight, are reliable ovals that hover above high-latitude regions like Alaska, Scandinavia, Siberia. But over the past 2 years, something's changed. Those ovals? They're stretching, drooping, slipping far farther south than they're supposed to. In October 2024, auroras were seen as far south as South Carolina, northern Italy, southern Japan, and even Mexico City. And not just faint whispers either. Full-spectrum auroras, clearly visible with the naked eye. People in Texas walked outside to find their sky pulsing magenta and jade. For most of them, it was magical. For NASA, it was concerning, because that kind of auroral visibility isn't supposed to happen without a major geomagnetic storm. And yet some of these events occurred during mid-level flares, storms that, on paper, shouldn't have had the muscle to light up those latitudes. It's the magnetic equivalent of a car alarm going off from a gentle breeze. NASA's updated auroral oval maps now reflect this new reach, expanding prediction zones further and further toward the equator. They're also adjusting their models of ionospheric conductivity, how well different layers of the upper atmosphere carry and transmit the electrical charges delivered by solar particles. The early findings? Earth's atmosphere might be more reactive than we assumed. Maybe it always was. Maybe we just weren't paying close enough attention. Historians still argue whether accounts of glowing red skies over ancient Rome and medieval Baghdad were misinterpreted auroras. Back then, people described sky fires and blood curtains. Some blamed gods, others blamed omens. A few blamed wheat. Hey, but modern scientists are starting to wonder, what if the sun was flaring harder, more frequently back then too? Here's a fringe tidbit for tonight's stargazing. Some researchers now believe that Earth's magnetic field isn't just weakening overall, it's becoming more lopsided. Think of a sphere with an off-center core. The South Atlantic anomaly, remember that from earlier? May be just one symptom. The result? Charged particles from the sun can sneak in at lower latitudes than ever before, carving temporary aurora highways where none existed before. And those highways? They aren't just light shows. They're pipelines for electric current, injecting energy into the ionosphere, and sometimes inducing ground currents in power lines below. You've probably never thought of the northern lights as a fire hazard, but during strong events, they can overload transformers, heat substations, and even trigger emergency shutdowns. In 2025, during a particularly vibrant aurora event seen across Central Europe, parts of the Czech Republic experienced local blackouts that coincided exactly with auroral peaks. The media blamed equipment failure. NASA issued a quiet technical note, ionospheric coupling event observed, which if you translate from science, basically means the sky lit up and the grid flinched. Want something weirder? A commercial airline flight over the mid-Atlantic experienced unexpected compass drift during that same storm. For 15 minutes, navigation instruments showed inconsistent headings. The crew switched to backup systems, rerouted slightly, and landed safely. When the post-flight report was logged under non-routine magnetic deviation, that's bureaucratic code for the aurora messed with our plane. Meanwhile, aurora chasers, the hobbyists who live for these ghost lights, have been noticing the trend for months. Forums lit up with reports of auroras in Kansas, auroras in southern France, even auroras over Cairo's outskirts, where they shimmered low on the horizon like a hallucination. NASA, to its credit, has started working more closely with citizen scientists to log these sightings, because the official monitoring stations can't be everywhere. And this auroral drift, it's not slowing down. If anything, the sun's charged breath is reaching farther every week. The deeper implication here isn't just pretty lights, it's magnetic vulnerability. When auroras show up where they shouldn't, it means the planet is absorbing solar energy in places it's not used to, energy that can impact aviation, communication systems, radio signals, and yes, human biology. Fringe science moment. A few neurologists and circadian rhythm researchers have started studying aurora-linked sleep disturbances. Their working theory? These light-heavy magnetic events subtly affect melatonin production in humans, even indoors. It's speculative, but intriguing. Some people report vivid dreams, strange headaches, or sudden insomnia on auroral nights, especially those far from the poles, where their bodies aren't used to it. And then there's the wildlife. Migratory birds, nocturnal mammals, even insects. All of them tune their navigation to subtle magnetic cues. With auroras flickering in unnatural zones, researchers in the UK and Argentina are reporting spikes in disoriented animal behavior. Moths migrating backward, birds circling unfamiliar skies. A farmer in Chile swears his cattle refused to leave their barn during an unusually strong red aurora. Maybe coincidence, maybe magnetism. All of it paints a quiet, glowing picture of a world that's changing, subtly but steadily. So next time someone tells you auroras are harmless, just pretty curtains in the sky, you might remember they're also data made visible, signs of solar energy hammering Earth's protective shell, electricity in motion, a system under stress. And you'll lie there remembering that green and purple sky from a viral post, thinking how beautiful it looked, how magical. But now you know better. That wasn't magic. That was the sun knocking at your latitude. You're deeper now, almost nestled into the sun's breath itself, where heat becomes structure and light becomes movement. And just ahead, like a ripple forming on a pond surface, you see something that doesn't make sense. There's no flare, no warning flash, but suddenly a massive solar wave ripples outward, flinging plasma in a sweeping arc. No precursor, no flare, no sunspot shout, just impact. Welcome to the eerie world of stealth CMEs and solar tsunamis. CMS, coronal mass ejections, are solar eruptions that hurl billions of tons of plasma and magnetic field into space. They're the heavyweight champions of space weather. When one hits Earth, it can compress our magnetosphere, so spark auroras, or, if big enough, cause real-world disruptions to satellites and power grids. Traditionally, these events are triggered by visible solar flares or sunspot eruptions. You see the flare, then brace for the CME. But lately, that rulebook isn't holding up, because more and more frequently, NASA is recording CMEs that don't follow the script. They appear suddenly. No significant flare, no sunspot precursor, just plasma, gone. These are the so-called stealth CMEs, a growing category of solar ejections that sneak off the sun with little to no surface warning. First identified back in the early 2000s, they were once considered rare, but during this cycle, they're increasing rapidly, and the really weird ones, They're accompanied by EIT waves, also known as solar tsunamis. These are fast, sweeping waves that move across the solar corona at hundreds of kilometers per second. Imagine watching a ripple spread across boiling gold. That's what NASA's Solar Dynamics Observatory is capturing. Beautiful, eerie pulses of coronal material surging outward from invisible sources. Historians still argue whether the great auroral storms of 1770, which lasted for 9 nights, were caused by a series of stealth CMEs. There were no sunspot records at the time, no flare logs, just written accounts of blood-red skies from Japan to Colombia. Some researchers now suspect those events were precursors to what we're starting to understand today. And here's the chilling part. Stealth CMEs don't give warning. By the time our sensors detect them, usually via coronagraphs on satellites like SOHO or Stereo, they're already on the move, sometimes less than 24 hours from impact. It's the space weather version of looking both ways before crossing and still getting hit by a car that was parked. NASA's been working hard to map these events, but the truth is our existing solar observation tools are tuned to flares and bright spots, not ghostly, slow-motion ripples that barely register in the light spectrum. These stealth ejections are often only visible in side view, seen from spacecraft not aligned directly with the Sun-Earth line. Which brings us to Parker's solar probe. That brave little craft is currently skimming the sun's outer atmosphere at record-breaking speeds, gathering data that may finally explain what's triggering these quiet outbursts. One theory? The sun's global magnetic structure is becoming more unstable, twisting not just in local spots, but in massive loops that reach across hemispheres. When those loops reconnect far beneath the visible surface, they may trigger CMEs with no visible flare. It's like watching an earthquake ripple through a cloud. You never see the fault line, just the shock wave. Fringe alert. One small but vocal camp of researchers now believes coronal dimming events, brief localized drops in solar brightness, may be stealth CME precursors. Not enough data to confirm it, but NASA has started cross-referencing dimming logs with CME detection events more seriously. The pattern's fuzzy, but not random. Back in July 2025, Earth was hit by a surprise G3-class geomagnetic storm that caused minor blackouts in parts of Scandinavia and disrupted marine GPS for hours. There was no visible flare beforehand, no alert issued, just a ripple spotted 18 hours prior on Stereo A, a coronagraph image so subtle it was missed during routine monitoring. And the post-event analysis read like an apology. Low-profile ejection underestimated, impact window revised retroactively. Translation? We missed it. It hit. We're still catching up. NASA has since expanded its data fusion protocols, combining readings from the Solar Terrestrial Relations Observatory, SOHO, Parker, and now even Solar Orbiter, ESA's flagship heliophysics mission. Together, these eyes are trying to triangulate stealth CMEs in near real time. But there's a problem. These events are subtle. Their signatures are easy to miss in noise. And when solar activity ramps up, as it has been, signal clutter makes detection even harder. The sun is spitting out so many small to mid-level events right now that our systems are struggling to tell which ones will blow past Earth and which ones will come right at us. In 2026 alone, when we've already had 3 stealth CMEs that caught systems off guard, and each time there's a scramble behind the scenes. Recalibrate, reroute, revise. Nothing dramatic, no satellites fried yet. But the trend? Worrying. Because if the sun can now fire without flaring, if CMS no longer come with obvious cues, then our early warning model is obsolete. You're lying there in the dark, perhaps remembering the last beautiful aurora photo that went viral. Magenta clouds hanging over Ohio, or red spikes glowing over Tasmania. Gorgeous, yes, but beneath every image is a silent rush of plasma, crossing space at millions of kilometers per hour. And maybe, just maybe, the one that causes the next Carrington-scale event will be a stealth. No boom, no blast, just a wave and a whisper. Yet you're drifting now in that uneasy space between wonder and warning, still wrapped in solar wind and auroral afterglow. But something's pulling at the back of your mind. A memory almost. A story you have heard once. Something about telegraph sparks, skyfire, and the day the sun punched Earth in the teeth. That wasn't fiction. That was real. And we might be due for a rerun. Welcome to the looming shadow of the Carrington event and the quiet debate over whether it's about to happen again. Let's rewind to September 1st, 1859. British astronomer Richard Carrington was observing sunspots through a telescope, projected safely onto a screen, because he wasn't insane, when he saw a sudden, blinding flash of light erupt from the surface. A solar flare, before anyone even knew what those were. Hours later, telegraph systems around the world burst into chaos. Sparks flew from machines. Operators were shocked. Some systems continued working even after being unplugged, powered solely by the geomagnetic energy storming through Earth's crust. That flare, and its accompanying coronal mass ejection, was the largest solar storm ever recorded. Auroras danced as far south as Cuba and Colombia. Miners in the Rockies woke up, thinking it was morning. And the modern equivalent? Well, we didn't have satellites or power grids back then. But if it happened today, NASA once estimated the global economic damage could reach $2.6 trillion and take up to a decade to fully recover. Let that sink in, which brings us to now. Because recently, NASA's solar observatories, Parker, SDO, Solar Orbiter, and the rest, have picked up magnetic field complexities eerily similar to the buildup before the Carrington event. Not a copy-paste, of course, but the kind of tangled, high-energy structures that could, under the right circumstances, unleash a similarly planet-scale burst. And while NASA isn't publishing press releases screaming Carrington 2.0, it's doing something more subtle, updating risk assessment language in its internal models. One document quietly reclassified the odds of a Carrington-level event occurring within the next decade as significant, a word that, in scientific circles, lands somewhere between worrying and please double-check the backup generators. Historians still argue whether smaller but similar events have already occurred and just missed. One near miss happened in July 2012, when a massive CME launched from the Sun in Earth's direction, except Earth had just rotated out of the way. That storm hit one of NASA's satellites instead. Had it arrived just 1 week earlier, we'd be living in a very different digital world today. Your phone? Fried. Your GPS? Lost. The internet? What's that? Fringe alert. Some independent researchers argue that 2012 wasn't a near miss. It was a dress rehearsal, part of a pattern that suggests Carrington-scale events happen more frequently than we like to admit. It's just that Earth usually isn't in the blast path, like dodging bullets by pure planetary luck. And the physics, they're there. During solar cycle 25, we've already observed more X-class flares in a shorter time span than in the same period during cycle 24. And remember, Carrington's flare was likely an X45, way off the scale we use today. The biggest modern flare, an X28 in 2003, briefly blinded solar sensors. Yes, blinded. The instruments literally maxed out. NASA has since rebuilt its sensors to better handle super intense bursts, but that X28 was still weaker than Carrington, which raises the question, if we haven't seen one that strong in 150 years, are we overdue? Some at NASA think so. Others argue that solar cycles are too chaotic to predict with confidence. The debates happen behind conference doors, in academic journals with names like Space Weather Quarterly and Heliophysics Abstract Digest. No headlines, no breaking news. Just a growing sense that the sun doesn't care about our models. Want a more grounded concern? Let's talk transformers, the huge metal beasts that power modern civilization. They sit in substations, while quietly managing the flow of electricity across continents. But during a massive geomagnetic storm, they can overheat, fuse, or melt. In 1989, a much smaller solar storm caused 6 million people in Quebec to lose power because one transformer gave out. Now multiply that by hundreds. The Carrington event's modern twin could cause cascading blackouts, long-term infrastructure damage, and knock out internet backbones. Satellites could be fried, financial markets disrupted, navigation systems scrambled. You'd survive. but your fridge, maybe not. NASA knows this, which is why they've partnered with FEMA, NOAA, and international agencies to quietly run Carrington scenario drills. You won't see those advertised, but they exist. Regional blackouts, communications failures, supply chain shocks. They're building contingency plans, even if no one's talking publicly about it. And yes, there's a protocol for astronauts too. If a Carrington-level storm were detected en route to Earth, astronauts aboard the ISS or any deep space mission would have only minutes to seek shelter. Current warning systems might catch it 15 to 30 minutes before impact, depending on whether a Type 2 radio burst is detected in time. And if it's a stealth CME, well, we've already talked about that. Now for the curious twist, in ancient ice cores drilled from Greenland and Antarctica, researchers have found nitrate spikes that match known solar events. One layer corresponds to the Carrington event, others, older, bigger. A 775 AD event, recorded in tree rings, may have been even more intense. No telescopes back then, but the trees remember. So you lie there, eyes closed, imagining a day when your lights go out, not from a storm on Earth, but from a breath of fire across space. The sun doesn't rage often, but when it does, it doesn't miss. And this cycle, it's feeling twitchy. So maybe, just maybe, Carrington's ghost is pacing again. You're floating backward now, farther from Earth and closer to a cautionary tale written in dust and silence. Beneath you lies a world once warm, once wet, once atmospherically alive. Mars, the red planet, a graveyard of lost oceans and shredded skies. And according to NASA's own spacecraft, it didn't always look this way. What happened? The sun, slowly, violently, consistently, the sun stripped Mars bare. And the lessons it's whispering, they're not just about Mars, they're about us. Let's start with the MAVEN mission, NASA's Mars Atmosphere and Volatile Evolution spacecraft. Launched in 2013, MAVEN was tasked with one job: figure out what happened to the Martian atmosphere. Why did a planet that once had rivers and clouds and possibly even life end up looking like a freeze-dried tomato? The answer, it turns out, is solar wind and time. Unlike Earth, Mars doesn't have a strong global magnetic field. It may have had 1 billion of years ago, but it's shut down, a planetary heart that stopped beating. Without that protection, the Martian atmosphere was left exposed, unshielded. The sun's charged particles slammed into it relentlessly for eons, stripping away molecules bit by bit, like sand blowing off a dune. What was once an atmospheric blanket became a whisper-thin veil. MAVEN confirmed it in 2015. Solar wind and radiation are the primary drivers of Martian atmospheric loss. During solar storms, MAVEN observed atmospheric escape rates increase tenfold. It wasn't just erosion, it was assault. Historians still argue whether ancient Mars may have hosted oceans and even primitive life before its atmosphere collapsed. Some believe early microbes could have thrived in shallow seas before the solar stripping began. Others think life, if it ever formed, didn't get the chance. And here's where it gets uncomfortable. Because while Earth has a magnetic field, for now, it's not immune. MAVEN's findings forced NASA to quietly reassess Earth's long-term resilience. No, we're not about to lose our atmosphere tomorrow. But if solar activity increases dramatically, or if Earth's magnetic field continues weakening, our upper atmosphere could face a slow, Martian fate. Fringe science? Not entirely. In fact, NASA has expanded MAVEN's mission scope to model potential long-term atmospheric degradation scenarios for Earth-like planets, including Earth itself. One of those models, leaked briefly during a heliophysics symposium, showed a possible future in which persistent solar storms, coupled with a weakened magnetosphere, could lead to measurable atmospheric loss within a few thousand years. That's nothing on a human scale, but geologically, it's a blink, especially if Earth's magnetic field continues to drift, decay, or reverse. And while we're on reversals, remember that our magnetic field has flipped many times before. The last full reversal was about 780,000 years ago. During the transition, the field didn't vanish, but it weakened, possibly by as much as 90%. If something similar happened again, and it overlapped with a solar maximum like the one we're in now, well, you might want to invest in some underground real estate. But let's come back to Mars for a moment, because the data coming from MAVEN isn't just about what Mars lost, it's about when. The mission found that the majority of atmospheric loss happened during the sun's early years, when it was young, hot, and far more violent. Solar output during the first few 100 million years of our solar system's life was intense, over 10 times the radiation Earth gets today. This means that for newly forming planets, timing is everything. Build a magnetic shield early, or your sky gets stolen. Mars, poor Mars, was a little too small and a little too slow, and now it's dust and dreams. NASA's learned a lot from this. When planning future missions to other planets, especially those in exoplanet systems, they now factor in stellar activity as a key habitability metric. Is the planet in the Goldilocks zone? Great, but does its star throw flares like tantrums? Not so great. MAVEN helps shape that thinking. It also helps shape human survival strategy, because NASA knows we're going to Mars. Not just robots this time, people. And if solar storms can strip an atmosphere, imagine what they can do to an unshielded astronaut on the Martian surface. Spoiler, it's not good. That's why newer Mars mission designs, like those from SpaceX and Artemis follow-ons, include underground habitats or regolith-covered shelters. Just a few meters of dirt can shield against solar radiation. You don't build that, you don't stay long. Fun fact, Mars still gets auroras. Not big ones, not polar ovals like Earth, but strange, flickering mini auroras centered over crustal magnetic fields, relics of the planet's dead dynamo. MAVEN captured images of them, ghost lights, faint reminders of the shield Mars used to have. Some scientists speculate that if Mars ever had intelligent life, it may have watched its sky fade away. One fringe theory posits that early Martian civilizations, if they existed, may have retreated underground, not just for warmth, but to escape increasing solar radiation. There's no direct evidence, of course, but MAVEN gave that idea a little extra fuel. And now here's the part NASA didn't highlight in their glossy public briefings. When Earth satellites observed that unusual high-altitude atmospheric compression event during a storm in late 2025, the same one that nudged the ISS radiation spikes, they referenced MAVEN data to compare escape rates. The upper thermosphere that week bled molecules into space at nearly triple the usual pace. Not catastrophic, not permanent, but measurable and worrying. Because if the sun's current storm levels are already having that kind of temporary effect, what happens if they get worse? NASA knows that Mars is a window into Earth's possible future. It's a warning that's not loud, not immediate, but deeply sobering. So as you lie there, listening to the hum of quiet space, imagine the wind. Not on your face, but through your sky. Imagine air being peeled away molecule by molecule, invisible fingers pulling the breath from a world. Mars can't stop it anymore. Earth still can, for now. You're sinking back down now, out of the Martian hush and toward a more familiar hum, a deeper buzz beneath your feet. Civilization, the grid, that woven web of electricity that powers everything from your blinking modem to hospital ventilators. And beneath it all, something flickers, twitches, because if the sun sneezes hard enough, the power grid shakes. And NASA, in quiet collaboration with energy agencies around the world, has been mapping out how fragile that grid truly is. Spoiler, it's not great. Let's start with the basics. When a strong coronal mass ejection hits Earth, it doesn't just paint the sky with auroras. It sends powerful currents of energy, geomagnetically induced currents, or GICs, surging through the ground. Those currents don't stay put. They slither up through metal, long conductors like pipelines, railway lines, and yes, power transmission cables. And when they do, transformers heat up, circuits stress, protective systems sometimes fail, and whole regions can, quite literally, go dark. NASA doesn't run the power grid, of course, but it plays a critical role in warning those who do. especially now as Solar Cycle 25 ramps into unpredictable territory. What's changed? NASA's latest models show that we've underestimated where and how deeply solar storms can affect our infrastructure. In early 2025, a collaborative mapping project between NASA, NOAA, and the U.S. Department of Energy quietly redrew the solar vulnerability map for North America. The results? Sobering. Regions once thought moderate risk were upgraded. Entire swaths of the eastern U.S., from Maine to the Carolinas, are now flagged as high GIC susceptibility zones, not because they're closer to the poles, but because of a nasty geological twist: bedrock conductivity. See, regions with shallow, resistive rock, like ancient Appalachian granite, don't allow electrical currents to dissipate easily. Instead, they force those currents up into the infrastructure, like a lightning rod stuck in stone. Historians still argue whether the infamous Quebec blackout in 1989 was the worst solar storm-related outage, or just the most well-documented. Either way, it took out power for over 6 million people in under 2 minutes. And that storm? It was 1/10 the intensity of the Carrington event. Now imagine that level of disruption across multiple modern power grids. Because unlike 1989, today's world is way more electrified and way more interconnected. Here's your quirky tidbit of the night. In 2024, researchers discovered that certain wind turbine control systems in the Midwest were briefly disrupted during a moderate geomagnetic event. The turbines didn't shut down, but their blade pitch control systems briefly desynchronized. The result? Power output spiked unpredictably, triggering momentary stress in nearby substations. It was a glitch, sure, but the kind that never used to happen. So what's NASA doing? They're feeding real-time solar wind and magnetospheric data into SWARM, the Space Weather Operations, Research, and Mitigation System. So think of it as a nerve center where solar data is fused with terrestrial infrastructure maps. When a flare, or CME, is detected, SWARM issues not just a general alert, but region-specific risk assessments, telling grid operators where currents are most likely to surge. One fringe debate? Whether private energy companies should be required to act on SWARM data. Right now, responses are voluntary. Some grid managers take proactive steps, rerouting loads, slowing down high-capacity lines, or isolating vulnerable substations. Others cross their fingers and wait, because prevention costs money and storms, until they hit, are invisible. And yes, they've already hit. In March 2025, a surprise CME, a stealth one, naturally, caused voltage irregularities across parts of the U.S. Northeast. No blackouts, thankfully. But transformer core temperatures spiked dangerously at 5 separate substations in New York and Pennsylvania. Engineers had to manually intervene to prevent damage. The public? Never heard a word. NASA logged it. Power companies issued vague equipment fluctuation statements, and the world moved on. But the truth? That was a warning shot. The global picture isn't better. South Africa's power grid has been flagged by NASA as particularly vulnerable due to long transmission lines running across old resistive crust. Parts of India and Brazil also show red on NASA's newest GIC risk maps. And then there's Europe. In 2024, a solar storm caused momentary frequency deviation in Germany's grid, an ultra-stable system. The deviation lasted less than a second, but was enough to trip multiple automated systems into brief, corrective action. And it wasn't a failure, but it was a wobble. And for high-frequency grids, that's terrifying. Some of the newest modeling, developed in tandem with ESA and the UK's national grid, now simulates grid-scale cascading failures triggered by solar storms. One scenario shows how a single strong CME hitting at peak load time could collapse 3 regional grids within 6 hours, triggering rolling blackouts across multiple countries. NASA's official line? Unlikely, but possible. But behind closed doors, engineers are preparing for grid triage. Strategies now include rotational brownouts during solar storms, fast line disconnects, and the deployment of new solid-state transformer systems designed to absorb or deflect GICs. Still, none of this solves the core issue. We've built our world on electricity, and that electricity flows through systems never designed to handle a furious star having a bad day. And here's a terrifying little footnote. Several key undersea internet cables are now recognized as potentially at risk, not from physical damage, but from shore-end power surges caused by ground currents during geomagnetic events. NASA doesn't oversee those, but submarine cable operators have been quietly added to swarm alert lists since late 2024. You lie there now, the floor beneath you humming with quiet, invisible current. Your home wrapped in wires and devices, all humming the same delicate frequency. And you realize you're not just under the sky. You're plugged into it. The sun doesn't care what's in your socket. But when it breathes hard enough, the surge comes anyway. And that map of weak points NASA built, it's growing redder by the day. You're still grounded, still tracing the buzz through your walls and wires. But tonight, let's shift perspective. Let's step away from the substations and satellites and talk about something older, something wilder. Because while NASA crunches data in sterile labs, something primal is already reacting to the sun's shifts. Something with wings, whiskers, instinct. Welcome to the quiet field of animal solar sensing. And yes, NASA's been funding studies. You probably already know that certain animals can sense magnetic fields. Birds, especially migratory species, use an internal compass, built right into their biology, to navigate thousands of kilometers without Google Maps. But what's less known and far weirder is that this compass can also act like an early warning system for solar disruptions. And in recent years, during spikes in geomagnetic activity, researchers began noticing strange behavioral anomalies in wildlife. Birds changing direction mid-migration, whales beaching themselves en masse, bees abandoning hives for days, and NASA, in collaboration with NOAA and a few surprisingly enthusiastic zoologists, decided to start listening. The result? A growing database of anomalous animal events loosely correlated with solar flares and geomagnetic storms. It's not conclusive. It's not clean. But the patterns are there, glimmering at the edge of our instruments, like auroras in the grass. In fact, some of the earliest hints came not from satellites, but from pigeon racers, a niche group with surprisingly precise flight logs. In 2023, a major UK pigeon racing league reported a 42% increase in flyaway events, birds that failed to return, on days with elevated solar activity. That same year, researchers in Japan documented erratic flight paths in tagged starlings during a moderate geomagnetic storm. Historians still argue whether strange animal behavior before solar storms is coincidence or instinct. Ancient Chinese records mention dragons flying low before celestial skyfires, possibly flocks reacting to atmospheric charge. And in Norse myth, the aurora was thought to be the glint of armor from ghostly riders. Romantic, sure, but also curiously aligned with magnetically disturbed nights. NASA's involvement, surprisingly hands-on. Starting in 2024, they funded a study through their Living with a Star program that uses GPS-tracked birds, ground-based magnetometers, showing in solar flux data to identify behavioral shifts before known solar events reach Earth. The fringe goal? To determine whether animals can detect precursor changes, shifts in the solar wind or magnetic field before our instruments can. It sounds like sci-fi, but some scientists think living systems might perceive subtleties that machines miss. For example, in 2025, just 48 hours before a stealth CME triggered auroras over South America, researchers in Argentina noticed a wave of nocturnal animal silence in their long-term acoustic monitoring data. Owls stopped calling, crickets quieted, the whole soundscape dipped. After the storm passed, the sound returned. Coincidence? Possibly, or perhaps those animals felt the invisible press of the sun's breath before it arrived. One species being studied closely is the loggerhead sea turtle. And these turtles use magnetic cues to navigate across entire oceans. But in recent solar events, hatchlings have been observed veering off course, sometimes by hundreds of kilometers. NASA is now working with marine biologists to log these deviations in real time using satellite trackers and, yes, solar storm alerts. You might think, that's fascinating, but what does it mean for me? Well, maybe nothing. Or maybe it means we've ignored a natural early warning system for centuries. One that chirps and crawls and buzzes before the sky starts glowing. A distributed biological sensor network with millions of tiny processors, feathers, scales, antennae, processing changes in ways we don't yet understand. And it's not just wild creatures. Domesticated animals have shown strange responses too. In Germany, researchers logged increased cow restlessness, more pacing, more vocalizing, during geomagnetic storms. In one 2024 case, a dairy farm noted a sharp drop in milk yield on the exact day of a solar flare. Again, not proof, but a pattern. One fringe theory posits that animals aren't just sensing magnetism, but subtle shifts in atmospheric electricity. The same shifts that might explain why some people claim to feel off during auroral nights, headaches, vertigo, strange dreams. Speaking of dreams, want a weird one? Some researchers have begun quietly comparing human EEG patterns to solar activity. Early results suggest mild but measurable changes in brainwave activity during intense geomagnetic storms. It's not brain control, it's not telepathy, but it might be a kind of ambient interference, a background buzz we haven't yet mapped. And NASA isn't leading that charge. It's too speculative. But the agency has acknowledged these fringe investigations in internal discussions. After all, if solar weather can bend metal, scramble signals, and shift migrating herds, why wouldn't it tickle our own biology? You lie there now, surrounded by silence. But outside in the grass, the air, the trees, something stirs. Maybe a fox sits still beneath a charged sky. Maybe a gull veers off course. Maybe a hive grows restless in the dark. The sun hasn't flared yet, but something is already responding. Something older than antennas. NASA's machines can hear the sun scream, but maybe, just maybe, Earth's creatures can feel it before it breathes. You're still lying there, mind gently floating through all the invisible whispers of the sun. But this time, it gets quiet. Too quiet, not peaceful. Not serene, but dead air. Black space. And if you were a pilot or a first responder, or even just a regular person tuning a radio, you'd feel it instantly. No signal, no warning, just radio silence. And the thing NASA's known for years, but doesn't like to say too loudly. That kind of silence is happening more often. Welcome to the unnerving world of solar radio blackouts, when the sun, ironically, screams so loudly in certain frequencies that it drowns out every other voice. Emergency broadcasts, commercial flights, Coast Guard calls, all silence under an invisible roar. Let's break it down. During a solar flare, the sun releases not only visible light and X-rays, but intense bursts of ultraviolet and extreme ultraviolet radiation. And when that radiation hits Earth's upper atmosphere, particularly the ionosphere, it rapidly increases the density of free electrons. This overcharged layer becomes radio opaque, especially in the high-frequency HF band, where a lot of long-range communication lives. What does that mean? If you're sending a radio signal from point A to point B via the upper atmosphere, like a pilot calling air traffic control across the pole, it might suddenly stop bouncing. Your signal goes up and vanishes. In aviation, they call it HF comms loss. In military ops, it's a potential tactical nightmare. In NASA reports, it's R1 to R5 class radio blackout, depending on how bad it gets. In March 2025, an X3 class solar flare triggered an R3 radio blackout that affected communications across the Pacific, when multiple commercial flights reported comms loss for up to 45 minutes. One flight en route from Honolulu to Tokyo was forced to switch to satellite backup while pilots manually verified waypoints. Passengers? Oblivious. But in the cockpit? Controlled quiet tension. And here's the twist. The flare that caused it wasn't even the biggest of the week. Historians still argue whether a series of WWI-era naval communication failures were caused by early solar blackouts. At the time, radio was still new, and signal dropouts were chalked up to equipment bugs. But logs from that era, compared with modern solar reconstructions, show a suspicious overlap with solar flare dates. Fringe detail of the night? Some amateur radio operators claim they can predict blackouts by watching sunspot behavior patterns before flares. Not satellites, not instruments, just sunspot geometry and a lot of old-school listening. One operator in Finland posts live blackout predictions on a blog that NASA analysts quietly follow. Officially, they don't endorse it. Unofficially, they're impressed. In April 2025, during a quiet solar week, emergency services in parts of northern Canada experienced sudden UHF dropout, short-range urban responder radio bands. Nothing catastrophic, but enough to delay communication during a fire response by several minutes. The public report blamed equipment interference. NASA's space weather log listed a Type 2 radio burst recorded just 14 minutes earlier. Let's talk about those bursts. When a CME moves through the solar corona, it can create a shock wave, like a boat pushing through water. That shock accelerates electrons, which emit specific radio frequencies as they spiral. These are Type 2 bursts, and they often precede or accompany blackouts. NASA's satellite system, SWPC, monitors them constantly, using spacecraft like Stereo and Wind to triangulate bursts in real time. But here's the problem. Those warnings sometimes come after the flare. That means comms might be gone before alerts go out. For aircraft over oceans or rescue crews in remote areas, that window matters. The sun in those moments is like a prankster smashing the intercom, shouting so loudly into the radio bands that no one else can talk. NASA's updated modeling now includes deep learning algorithms trained on flare and blackout patterns, trying to squeeze extra minutes out of what little warning time we have. Because a flare strong enough to cause an R4 or R5 blackout doesn't just affect aviation. It can knock out ground communications, jam navigation systems, and even cause temporary loss of signal on low-orbit satellites. And yes, that's already happened. In June 2025, a network of GPS-guided construction equipment in Nevada suddenly reported positional errors. The sync signals went haywire for 6 full minutes. No damage, thankfully, just confused backhoes and a lot of blinking diagnostics. But that same hour, NASA logged a mid-latitude radio blackout affecting the 5 to 15 megahertz range. Even marine traffic gets hit. NOAA ships in the South Atlantic have reported bursty, unexplained comms dropouts on days that just happened to coincide with minor solar flares. Want a darker twist? There's a quiet protocol now embedded in several national emergency alert systems that switches key frequencies during flare conditions. You'll never know it happened, but your weather radio might suddenly hop from one band to another without you touching it. That's not a bug. That's an evasive maneuver. But the really unsettling part? We're still not sure why some flares cause complete blackouts and others, often stronger ones, don't. NASA's heliophysicists are currently investigating the idea of ionospheric preconditioning, where prior flare activity softens up the atmosphere, making it more prone to absorb subsequent blasts. It's like setting kindling alight with a single spark after a week of slow drying. You lie there, maybe with the hum of a fan in your ears, maybe silence, and somewhere, up in the ionosphere, a wave of ultraviolet radiation is punching through at the speed of light. For a few minutes, the sky becomes opaque to certain signals. No calls, no echoes, just the hiss of nothing. And when it passes, the radios start working again, as if nothing ever happened. But the next one might last longer. The next one might hit during something that can't afford silence. Because when the sun yells, Earth stops talking. You're adrift now in a slower current, riding back through layers of time. Because tonight we're not just talking about flares or flight paths. We're digging deeper, literally, down into ice, into ancient tree rings, into the memory of the planet itself, where traces of long-forgotten solar storms are frozen like fingerprints in the dark. Because before there were satellites, before Carrington even squinted through his telescope, the sun was already flaring, already raging. And now, thanks to NASA's quiet collaboration with climate scientists and geologists, we know that some of those ancient storms were bigger than anything we've ever seen. And yes, they left clues behind. Let's start with the ice cores. Deep beneath Greenland and Antarctica, teams have spent decades drilling columns of ice going back hundreds of thousands of years. Each layer of snow, compacted into ice, carries whispers of the atmosphere at the time it fell, tiny bubbles of trapped gas, trace elements, even radiation markers. In 2012, scientists studying these cores found sudden spikes in nitrate and beryllium-10 isotopes, signatures of cosmic radiation bombardment. Most of the time, these levels rise gradually, but in a few layers, they jump violently over a very short period. Translation? And a colossal solar storm. One of the biggest spikes occurred around 774 AD, a moment now known as the Miyake event, named after the Japanese researcher who first identified it. Tree rings from that same year across Europe and Asia showed abnormal levels of carbon-14, a marker that suggests a solar particle event at least 10 times more intense than the Carrington event. That's not speculation. That's data. Quietly terrifying data. NASA, which helped fund some of the satellite calibration used to date these radiation spikes, has since taken a keen interest. Not because it loves history, but because this kind of storm happening now would be catastrophic. And here's the kicker. The 774 event didn't leave any historical record of auroras or skyfire in most regions. No collapsed civilizations. Just quiet, wet, terrifying evidence buried in the bones of trees and glaciers. That suggests it may have been a stealth solar particle event, less visible, but far more penetrative in terms of radiation. Historians still argue whether ancient texts describing blood-red moons or the sky raining fire might have been poetic accounts of such events. Some scholars point to fragments from the Anglo-Saxon Chronicle or Japanese court records, noting the heavens glowed strangely in that very year. But even stranger, it wasn't the only one. A second major spike, possibly even bigger, was found in ice cores dated to 993 AD, and another less severe, around 660 BC. These aren't one-off flukes. They're part of a pattern. The sun, it seems, throws megastorms every few hundred to thousand years. We just haven't been around long enough technologically to notice. Until now. Here's a fringe tidbit. A new collaboration between NASA and Japanese and Scandinavian researchers has begun scanning medieval church beams and ancient driftwood from Viking settlements. Why? Because tree rings record carbon-14 changes with yearly precision. And by studying more of them, scientists hope to build a detailed millennia-spanning solar activity timeline. The preliminary results? There may have been 4 to 6 major solar events in the last 2,000 years that dwarfed anything we've seen since we started using radios. NASA's biggest concern is the speed of these events. Some storms, like Carrington, gave a day's warning, but others, like the 774 AD event, may have hit Earth within hours of eruption based on how sharply the isotope levels jump. That's not enough time to shut down the grid or move astronauts, or reorient satellites. It's like watching a time bomb tick for 1,200 years and hoping it doesn't go off again while you're on Wi-Fi. And yes, those same ice cores contain more than just radiation stories. They also capture the climate response to space weather. In some cases, strong solar activity correlates with regional cooling or brief, sharp weather anomalies. Why? Possibly because of changes in stratospheric chemistry or shifts in cosmic ray cloud seeding. Yes, that's a thing. NASA's Jet Propulsion Lab has been experimenting with models that simulate how large solar storms affect ozone concentration, jet stream behavior, and even monsoon cycles. It's not solid science yet, but the implication is there. Solar events don't just hit tech. They may brush against biology and climate too. Let's not forget the magnetic reversals. Remember back in Section 6, how we talked about Earth's weakening magnetic field? Well, some scientists now believe ancient solar megastorms may have timed themselves to those periods of magnetic instability. One model, recently circulated in a heliophysics roundtable and quietly funded by NASA, suggests that solar superstorms may preferentially occur during declining magnetic epochs. If that's true, then Earth's current magnetosphere, which again is weakening and wobbling, could be approaching prime time. You lie there now, the floor beneath you cold, and somewhere below your feet is a mile of ice that once caught a cosmic scream. It's all still there, etched in molecular memories. The sun flared, the sky burned, and Earth survived. But back then, we didn't have power plants, or planes, or anything that could crash. Now we do. When in NASA is trying to build predictive algorithms based on the ancient record. The hope is to use the past to warn the future, to know not just if another Miyake-level event will happen, but when and how to respond. Because the real fear isn't that the next superstorm is coming. The fear is that it already left the sun, and we haven't seen it yet. You're floating closer now, not just in time, but in distance. This isn't metaphor anymore. You're circling the very edge of the solar inferno. And you're not alone. Because for the first time in human history, we've sent emissaries straight into the storm. NASA's Parker Solar Probe and ESA's Solar Orbiter are out there, riding the breath of a star. And what they're sending back? It's bizarre, unsettling, and not quite what we expected. Let's start with Parker. Launched in 2018, a Parker Solar Probe was built for one mission: touch the sun. Not literally, of course. There's still 6.5 million kilometers between it and the core, but that's inside the corona, the sun's outer atmosphere. It's like flying through a bonfire while measuring the wind. The probe is shielded by a carbon composite heat shield that can withstand over 1,370 degrees Celsius. Every few months, it slingshots around the sun, getting closer, faster, and bolder. It's already traveling faster than any human-made object, over 690,000 kilometers per hour. But speed is just the beginning. Because what it's seeing out there? The sun doesn't behave like we thought. For decades, solar models assumed the sun's magnetic field lines were smooth, symmetrical, spiraling outward in gentle waves. The so-called Parker spiral, named after the same Eugene Parker who inspired the probe. But the real data? The magnetic field switches direction abruptly in sharp zigzags called switchbacks. These are kinks in the solar wind, jolts of reverse polarity that twist through space like whip cracks. They weren't supposed to exist, and now Parker is finding hundreds of them. Some scientists now believe these switchbacks may play a major role in heating the corona, that strange mystery where the sun's atmosphere is hotter than its surface. Others think they're tied to flare precursors, tiny reconnections that build up like sparks in dry grass. Either way, NASA wasn't expecting to see this many, and certainly not this deep in the sun's breath. Historians, if you can call them that in heliophysics, must still debate whether early solar theorists underestimated the chaotic turbulence of plasma under intense magnetic strain. We assumed the sun was wild, but not this wild, not this layered. Now let's talk about Solar Orbiter. Jointly operated by the European Space Agency, ESA, and NASA, this spacecraft is following a different trajectory, out of the plane of the solar system. Its goal? To image the sun's poles, something no mission has ever done before. Why is that important? Because the sun's magnetic field flips every 11 years. The polar regions play a key role in that reversal, but we've never seen them up close. Solar Orbiter is giving us that perspective, slowly building a three-dimensional map of the sun's magnetic machine. And already it's revealed strange features. Campfires, tiny solar flares that pop off constantly, too small to be seen from Earth. They're everywhere, like static electricity dancing across the surface of a balloon. They may be one of the missing links in the mystery of coronal heating, or they may be something entirely new. In 2025, Solar Orbiter captured a sequence of eruptions near the southern pole that defied flare classification. They weren't large enough to be full CMEs. They weren't radio loud enough to trigger alarms. But they moved fast, and they carried structured magnetic signatures. NASA's internal report referred to them as quasi-ejective events, a fancy way of saying, we don't know what these are, but they look like trouble. And then there's the plasma dust layer. Both Parker and Solar Orbiter have confirmed that space near the sun isn't empty. It's cluttered, not with debris, but with a surprisingly dense band of charged dust particles slowly evaporating under the sun's gaze. This dust was once thought to be a minor factor. But now, it may be shaping the solar wind itself, affecting how energy flows outward from the sun, like wind dragging through sand. One fringe idea gaining ground is that this charged dust may interact with stealth CMEs, either hiding them from our instruments or altering their velocity. It's unproven, but Parker's data suggests some ejections decelerate or warp when passing through dense dust lanes. Like ghosts passing through fog. And yes, there's more. In mid-2025, Parker flew through a magnetic bubble unlike anything previously seen. For 11 minutes, all readings flattened. Magnetic field variation dropped to nearly zero. Plasma density dipped. Instruments blinked. It was as if the probe passed through a magnetic vacuum, a dead zone in the sun's breath. NASA dubbed it a null sheath. It might have been a rare feature of the solar wind, or the outer edge of a failed CME, or something else entirely. One researcher compared it to finding a cave in a hurricane. What does it mean for us? Everything. Because until now, we based our space weather forecasts on assumptions. On a version of the sun that was mostly linear, mostly smooth, mostly loud when it was about to throw something. But the real sun? It's sneaky, patchy, full of microstructures and rogue waves that twist through space with little warning. NASA's Mission Control has already begun integrating Parker and orbiter data into flare forecasting algorithms. Early trials suggest they can now predict switchback zones, areas where the solar wind may bend or intensify unpredictably. It's not perfect, but it's better than guessing. And the ultimate goal? Use real-time solar probes to give Earthbound systems more lead time, more hours, maybe even days. Because the future isn't just about watching the sun from afar, it's about flying into it and listening. And what Parker hears, even in the chaos, is structure. Not peace, not harmony, but a pattern of madness. So you lie there now, knowing that above your sky, two tiny machines are circling a star that still surprises us, still hides things, still speaks in plasma tongues we barely understand. And when the next great storm comes, chances are Parker will see it first. Let's hope we're listening. You're hovering now at the edge of insight, either orbiting between revelation and restraint, because tonight, after everything we've seen, measured, and barely understood, there's still one big question left hanging in the corona. Why isn't NASA saying more? Why the whisper campaign? Why the quiet updates instead of full-throated public warnings? Welcome to the disclosure dilemma, where science, politics, and risk management orbit each other in awkward silence. NASA, like any scientific agency, walks a tightrope. It exists to inform, to prepare, but also to reassure. And solar data, it's touchy, too technical for most headlines, too uncertain for definitive timelines, but too important to ignore. Over the past few years, especially since Solar Cycle 25 started going rogue, NASA has revised internal threat models, updated infrastructure vulnerability maps, and accelerated mission briefings with defense, energy, and aerospace sectors, all without triggering a single mainstream news wave. Why? Because saying too much about the sun's increasing unpredictability could cause cascading reactions. Markets, politics, public fear, even strategic military responses. In short, it's complicated. Let's take a step back. NASA's Space Weather Coordination Group, a multi-agency body that includes FEMA, NOAA, the Department of Homeland Security, and sometimes even the Department of Defense, meets regularly to review solar threat assessments. Most of these sessions are closed door. The reason? Many of the outcomes don't involve clear action steps. The data's fuzzy. The predictions are probabilistic. No one wants to cry flare and then have nothing happen. And yet, something is happening. In 2025, when NASA quietly shifted several long-term solar forecasts from low to moderate to elevated risk. You won't find this change in a headline. You'll find it in footnotes to technical summaries, mission briefings to aerospace contractors, or buried in logs from heliophysics panels. Historians still argue whether public information suppression around the 1989 Quebec blackout delayed broader awareness of space weather threats. Some say the power companies lobbied for silence. Others say the science simply wasn't ready. But today, with real-time monitoring, advanced satellite arrays, and a historical record full of warnings, we know better. And yet the messaging remains gentle, cautious, framed in words like resilience, adaptation, and preparedness. One former NASA data scientist, now working in the private sector, he described it like this: "We're on the brink of having to tell the world, hey, the sun's doing things we didn't expect, and we can't stop it. But don't worry, we've got a plan. And the plan? Hope we get lucky. There's a real concern that full disclosure, especially about increasing frequency of stealth CMEs, Earth's weakening magnetosphere, and rising spacecraft anomalies, might be misinterpreted as alarmism, or worse, spark reactionary policy changes based on incomplete science. So instead, we get quiet breadcrumbs, a new NASA webpage explaining space weather basics, an ESA infographic on flare strength shared with zero fanfare, an uptick in outreach materials sent to school systems and amateur astronomy clubs. Fringe detail: several government agencies, including the FAA and NOAA, may now receive solar storm briefings classified at a higher security level than before 2024. It's not because the data itself is secret, it's because the potential infrastructure implications are considered sensitive. There's also the military factor. Satellites, missile systems, radar arrays, many of them rely on precise timing and data flows that solar storms can interrupt. The Department of Defense doesn't just track solar activity, it's one of the biggest consumers of real-time solar monitoring data. And when NASA started flagging an increase in stealth CME activity, several military branches initiated quiet policy reviews about operational timing and satellite redundancy. You didn't hear about it, but it happened, and this isn't just an American silence. The European Space Agency, JAXA, and Roscosmos have all been updating mission profiles to account for higher-than-expected solar activity. Japan's HTVX cargo ship to the ISS carried enhanced shielding. ESA's Mars missions quietly adjusted launch windows for solar minimum overlap. No press releases, just smart moves made quietly. So what's NASA's actual plan? Internally, there's been talk of a threshold event, not Carrington level, something smaller, a significant enough storm to cause temporary disruption, but not mass panic. Something the public notices. GPS goes weird, auroras in Miami, a big blackout or flight delay, followed by a well-managed recovery. That would become the moment to pivot the narrative. This is what a solar event looks like. Here's what we know. Here's what we're doing. And yes, it could have been worse. It's like waiting for the fire alarm to go off so you can give a fire safety lecture afterward. NASA has dozens of working groups drafting response language, scenario simulations, and post-event educational materials, just in case. They've even filmed preliminary PSAs explaining what to do if your power goes out during a geomagnetic storm. They're just not airing them. Yet. The logic is understandable. It's hard to tell people the sky is unstable without sounding apocalyptic, especially when you can't give a date, especially when the same sun that powers life is also capable of frying it. Emotionally, it's too much contradiction. And so, the disclosure dilemma remains. Say too much and you risk panic. Say too little and you risk being unprepared. NASA is threading that line, foot by foot, flare by flare. You lie there now, your screen glowing gently, and above you, a star pulses with information, sending electromagnetic ripples through space, through systems, through the very shape of our civilization. And the people watching it most closely? They're whispering louder every day. You're here now, still, breathing, listening, orbiting the end of this long, glowing arc through fire, silence, and static. After all the surges and signals and secrets, we arrive not at catastrophe, but at you, your part in this solar story. Because no, you can't stop the sun, but you can prepare for what it's sending, quietly, calmly, without the doomsday bunker aesthetic, without needing to wear a tinfoil hat shaped like a parabolic dish. Let's get one thing straight, you're already affected, even if your power's never flickered. Even if your GPS never led you to a lake instead of a coffee shop. If you've ever seen an out-of-place aurora, or had your plane delayed due to road congestion near the poles, or heard your radio crackle with nothingness, congrats. You've been brushed by space weather. So what can you do? First off, know when the sun is acting up. NASA and NOAA both provide real-time solar activity updates through services like SWPC, Space Weather Prediction Center. You don't need to memorize X-class thresholds or learn how to read coronagraphs, but having a general awareness, like checking the forecast, means you won't be surprised when weirdness happens. There are even apps now that deliver solar flare alerts straight to your phone. Not just for science fans or doomsday preppers, for pilots, ham radio operators, satellite internet users, even amateur photographers chasing auroras, and most of them are free. One of them probably already lives on your app store. Next, protect your tech, not with a Faraday cage, unless you're into that, but with some basic habits. Use surge protectors for essential electronics. Not just for lightning storms, some solar-induced surges can slip through the grid. Keep critical devices charged, especially during known geomagnetic storms. Back up your important data, locally and in the cloud. Flares don't typically fry your phone, but they can corrupt satellite data streams. Airline traveler? Pay attention to flight path changes, especially on long-haul or transpolar routes. Increased solar activity can trigger sudden reroutes, added delays, or temporary radio silence over the poles. It's not fear, it's logistics. And if you use GPS for work, surveyors, drivers, drone pilots, farmers, know that high solar activity may affect precision. Even a 1-meter drift can throw off automated equipment. On those days, be old school. Use manual tools, cross-check coordinates, take a breath. Speaking of breath, solar storms can affect your body too, subtly. You may feel more tired or headachy or emotionally off. Not everyone does, but if you do, now you know why. It's not magic, it's magnetism. Fringe tip? Animals may sense solar events before we do. If you live in a rural area and your livestock or pets suddenly act weird before a flare is announced, you're not hallucinating, you're observing. Log it. Compare it to space weather data. You may surprise yourself. Emergency preparedness? You don't need to build a vault, but it's smart to have. A battery-powered radio in case of widespread communication disruption. A basic emergency kit with water, food, flashlights, and first aid. A printed list of important contacts because phone batteries can't store memory if the power's out. NASA and FEMA both recommend this, and not just for solar events. Hurricanes, ice storms, infrastructure hiccups all use the same playbook. And if you're someone who runs a business that depends on timing, location, or satellites, banks, logistics companies, emergency services, consider integrating space weather forecasting into your risk model. It's not a fringe science anymore. It's operational reality. And finally, don't panic. That's not a slogan. That's a philosophy. Solar storms are part of life on Earth. They've always been here. We're just now smart enough to see them. You've lived through hundreds already. You're not powerless. You're simply participating. The sun is not your enemy, but it is your neighbor. And like any good neighbor, it occasionally throws wild parties you weren't invited to. You don't have to leave the building. Just check the hallway before you open the door. NASA may not issue sirens every time a flare flies, but you're not helpless in the dark. You have tools, awareness, curiosity, and now a better sense of what's actually going on up there. You lie there quiet, but awake. Somewhere overhead, satellites reposition. Planes curve gently off course. Your phone signal flickers. The grid hums. And the sun keeps whispering. Not with malice, not with intent, just with energy and pressure and time. Your job is simple. Listen. Prepare, adapt, and maybe, just maybe, watch the sky glow green over your driveway one night and smile instead of worry, because now you know what it means. Word count, 1,101. Wind down, approximately 300 words. So now we rest. The sun continues to churn overhead, but here, on this quiet side of night, you're safe. You've walked through magnetic storms, sifted through ice cores, floated beside spacecraft, and watched the sky fold into colors it was never meant to show. You've seen silence, heard flares, understood the weight of a whisper in a solar wind, and through it all, you remained. No alarms, no panic, just the knowledge that Earth has weather, space weather, and you are part of that dance. A small part, but still a part, connected to satellites, birds, auroras, and ancient rings of Arctic ice. Linked to astronauts and algorithms and sleepy cows who feel the storm before the sensors blink red. So exhale. The fan hums gently. The grid holds for now. Your phone rests untouched. Outside, the stars may shimmer a little differently. The air might carry more electricity than usual. But it's okay. You're ready, not for apocalypse, but for awareness. The sun breathes, Earth listens, and tonight, so do you. Now drift. Let your thoughts settle like ash on calm solar wind. Let sleep find you under a sky that glows not with danger, but with beauty. And remember, you are stardust, protected by magnetic skin, cradled by science, satellites, and soft human curiosity. The light will still be here when you wake,